Hello, welcome back from lunch. We're a few minutes past the reconvening time, and so in the interest in staying on schedule, we'll let people filter in. I think most people are back. And it is my honor to introduce this session. David Ho is going to kick us off. I told him he has to explain this meme because I don't understand who's supposed to be right. Is it the grandma supposed to be right? But and we have a great session lined up. David will be first, and then Galen will follow up, and then we'll have a panel discussion after that.
So grandma is always right. So I should say that I'm very happy that this meeting is happening. Last year, I tweeted this about the need for MRV in Ocean CDR, and I got a lot of pushback. People sending me angry emails about this. So it seems like we've come a long ways from that time. So I'm David Ho. I'm from University of Hawaii. And so full disclosure about all the companies and organizations that I have a relationship with. I work for Carbon Direct, which a lot of you know. I've worked with Stripe on some of their MRV stuff. I was paid by Ocean Visions to work with Matt Iserman and Brendan Carter on their project, CMate, which is now Ebb Carbon. And I am a reviewer for X Prize carbon removal. And that's all I'm paid for. And I've talked to various people. But, okay. So here are my take-home messages. Just like Matt, if you fall asleep, at least you'll know what I talked about. And I think that knowing air-sea fluxes is essential for Ocean CDR. And I'll show you that we have field techniques to determine gas transfer velocities and air-sea CO2 fluxes on sort of relatively short time scales, on the order of weeks, and small spatial scales, so tens of kilometers. And these field techniques, I think, are hard to implement for MRV because of the long time scales and large spatial scales involved. And I think that sensors and autonomous measurements alone will not be the solution because of what they can't measure, because of their lack of accuracy and precision, and because the water moves around. And so, I put together this talk before I saw any of the other talks. So this sort of reiterates what Matt Long said earlier. I think for MRV of Ocean CDR, we need a combination of field process studies and numerical models and some way to generalize that, maybe using either machine learning or statistical models. Okay. So here's the outline of my talk. I'll give an intro, talk about the relevance of air-sea fluxes to MRV, and I'll show you how we measure these fluxes and talk about what I see as some of the challenges. So start very basic. This is the basic flux equation. Like the air-sea flux of any gas, CO2, is determined by a kinetic term, the gas transfer velocity, and the air-sea concentration gradient, or the thermodynamic driving force. So if either of those is zero, you have no flux. And both of those things can be measured in the field. And so to calculate on a global scale, interannually or even monthly, what the air-sea CO2 flux is, we can take data from satellites of a global wind field and a relationship between wind and gas transfer velocity, and then take some global field of the partial pressure of CO2 and determine the air-sea CO2 fluxes. And that's, the sort of database method to do that. So in terms of the relevance of air-sea CO2 fluxes for CDR and MRV, there's this paper by Jim Orr and Jorge Sarmiento that was published in 1992, so quite a few years ago, and it's gotten something like 30 citations. And that's sort of shocking for a paper by Jim Orr and Jorge. And partly it's because they published it in this obscure journal called Water, Air, and Soil Pollution. But it's about the potential of kelp for CDR, basically. And they have this important message in there, what I think is important, at least for our meeting, which is that just because you remove CO2 in the water, that is not CDR. And all the carbon that's lost from the surface layer, it's not replaced one-to-one by CO2 from the atmosphere, right? So that's really important. So we need to figure out how much CO2 actually comes in to replace what you've done in the water. And I like this figure from a paper that was published this year by Hurd et al. And Leonard Block is a co-author on this. So on the x-axis is time, and on the y-axis is this seawater CO2 concentration. So you've done some treatment and you've lowered the CO2 in the water. So you draw down the CO2. In this case, it's by kelp, but you can imagine it's by OAE. But that is not CDR, right? You've just drawn it down from the water. It's really the second step where the water comes in to replace what you've reduced. That's the CDR part. And the rate at which that happens then depends on what happens to the water mass and what the gas transfer velocity is and carbonate chemistry and so on. So that's why air-sea fluxes are relevant. Okay, so how do we measure this? So we have two main techniques, two main field techniques. One is what I've done a lot, which is you go out there and you inject two tracers. I'll explain it this way. So if you want to determine, let's say, the gas flux in your bathtub, well contained, you put a tracer in there, it's well mixed, you sample it over time, and the tracer will decrease. And you know that that's due to gas exchange. But if you do the same thing in the ocean, you'll have dilution. And to take care of the dilution component, you could put maybe a conservative tracer that's not volatile, like some sort of dye. And then you take care of that dilution part and you can get the gas exchange. But we don't have such a tracer, right? The dyes only last for a day or two. So we use two volatile tracers, two gases that have very different diffusivities. So helium diffuses an order of magnitude faster than SF6. So you can imagine dilution doesn't change the ratio between the two, but gas exchange will, because helium will go out much faster than the SF6. And what I've just said to you is described by this equation up there. And that's how it works. And so after we inject the tracer in the water, together, we map it out. Sometimes we put a buoy in the center, but invariably it'll drift out of the patch because things are terrible at staying with the water. But we try to map out the tracer with onboard analytical systems. And then you can visualize the tracer. And we've done this in various parts of the coastal and open oceans. And here's a plot of wind speed versus gas exchange. So we think that wind speed is the dominant driver for gas exchange because it creates turbulence and bubbles in the water. And you see this nice relationship between wind speed and gas exchange. And these are the various points that we've gotten from these different experiments in different parts of the ocean. The other method you've heard about earlier this week is eddy covariance. So eddy covariance was developed on land over cornfields in Iowa or Kansas. And then now people apply it in the ocean. It's more complicated because you have a moving platform and there's flow distortion and so on. But the principle is the same. You look at the covariability between the vertical velocity of the wind speed and the gas concentration, and you measure it at 1 hertz, one sample per second. You average it to 20 minutes, and you try to figure out where the footprint of your flux is coming from, and you get a flux. And here's a synthesis by Yang that's published this year of some different cruises that they've done in different parts of the ocean. And you see the same general relationship. And there's a gray line on there, which is my parameterization of wind speed and gas exchange from dual tracer. So the two methods roughly agree, right? And you have the same sort of relationship between wind speed and gas exchange. Okay, so everything seems great, seems peachy. What are the challenges in quantifying CO2 uptake? Well, it starts with this this problem that air-sea CO2 equilibrium takes months. And Kara showed this paper from Danny Jones from 2014, where they show that the mean of the uptake rate, I guess, or uptake time is like 4.5 months, right? But there's a range from half a month to 2 years, depending on where you are in the ocean. And that depends on your mixed layer depth, depends on the gas transfer velocity, the Ravel factor, and this ratio between DIC and aqueous CO2. And so also, I showed this nice relationship between wind speed and gas exchange. But when you go to some coastal areas where CDR projects are likely to be deployed, there might be other factors that affect gas exchange, like surfactants or difference in wind fetch and bottom generated turbulence that might also play into it. So we might not know gas exchange as well as we think. It's difficult to track a water mass over a period of 4 months, let alone 2 years, right? It's hard enough to do it for 2 weeks, okay? And autonomous instruments are not Lagrangian. They don't follow a water mass, okay? And they're not accurate and precise enough to detect fluxes and changes in inventories. And I'll try to convince you of all these things. So how well do we know gas transfer velocities? Here's a paper, a seminal paper by Wally Broker, where they constructed an inventory of bomb radiocarbon in the ocean. And they have this one point, this whole ocean bomb radiocarbon inventory. And they've related it to the, he calls it the piston velocity, basically the gas transfer velocity that's necessary to create that inventory. And he's plotted it versus the mean wind speed. And being Wally Broker, he fitted a quadratic through one data point, okay? And there it is. So how well did he do? So the red line is Wally's point. So I joke that, most of us are spending our entire careers showing what he's shown with one data point, right? So do we know gas transfer velocity very, very well? Well, so there's this figure that Jessica showed at the beginning of this meeting that I had tweeted about, and Matt showed it again today, that shows this huge difference between data-based methods to estimate the ocean carbon sink and model-based methods. And so, I had said that this is equal to more than 900,000 orca plants worth of CO2, right? And so maybe we don't know the gas transfer velocity as well as we do, or maybe there's something wrong with models, right? But fortunately, I think we know where the issue is. And if you look at the breakdown for different ocean basins, the problem occurs in the Southern Ocean. So I think we can probably get at that, but it does mean that, we have to be careful about how much we trust, database methods or models, right? We just have to be aware of that. And then this idea that of water masses being difficult to track, and water is going to move around. Like when you deploy your alkalinity enhancement, or when you grow the kelp, the water, unless you anchor your kelp, well, the water is going to move. And I show you two tracer patches from this experiment called the Southern Ocean Gas Exchange experiment, where the first one moved over 40 kilometers in just 6 days. So in less than a week, it moved 40 kilometers. The other one moved 78 kilometers over 15 days. And it took a lot of effort to track this and to map it as it spreads out. And we're not going to be able to do this over the entire deployment of any of the ocean CDR techniques. And then, you might say, well, what if we could measure the flux from eddy covariance? So on the right side, you see, so this is also from Southern Ocean Gas X. You see these blue points that have been averaged direct covariance fluxes, and it looks pretty good, nice trend. But if you look on the left, these are individual data points. So they're individual in the sense that they're the averages of 1,200 measurements already. So it's the average of a lot of measurements, and it's a mess, right? So these are individual flux measurements. And so flux measurements over the ocean are quite messy, and because of instrumental issues and because of a lot of corrections that you need to make for water vapor, for motion, for flow distortion. And then maybe you have some heterogeneity in your fluxes as well. So it's probably not the way to go. Plus, you're not going to follow, your patch around for months measuring fluxes. And just a thought exercise. So Lin, in his lightning talk, enhanced the alkalinity by, I think, 20 micromoles per kilogram. So here, I start with a tank of water. I enhance it by 10 micromoles per kilogram. And then, so that's not CDR, right? CDR is when the CO2 is taken up. Then, your delta PCO2 is back to 0. And you have this enhancement in DIC of about 6 micromoles per kilogram. And then a change in pH of 0.002. And as Andrea Sutton showed you, we don't have instruments, autonomous instruments to measure DIC. We can measure PCO2, we can measure pH, but we're not going to measure pH to that level, on top of the variability. So that's 10 micromoles. If we do 30, you have 0.005 instead of 0.002. That's still really hard, even if you could get your instruments to follow the water mass exactly, which they're not going to do. It's a really tough measurement to make. And then I picked 10 and 30 because if you look at this modeling study that was done on the Great Barrier Reef, where they did a continuous release of 90,000 tons of alkalinity every 3 days for 1 year. Okay, let that sink in. 90,000 tons every 3 days for 1 year. You get this enhancement of, in some places, up to 30 micromoles per kilogram. So it's already a huge signal. I mean, it's a huge amount of alkalinity to put in. It's a huge signal, and I don't think we will be able to detect it. And then you say, well, what if we went out there and measured the IC? So there's this paper by Rick Wanikoff from 2013 that showed that the decadal change in ocean inventory DIC, right now the ocean's taking up about 10 gigatons of CO2 every year. So that's 100 gigatons of CO2, okay, taken up by the ocean. We can't see that. So the best carbon chemists cannot measure with confidence this increase, right? So they show that if they measure the PCO2, they can see it. But this is a measurement that nobody makes, this discrete PCO2. You can make sort of underway PCO2 at the surface, but sort of column PCO2 is not made. But this is a huge amount of DIC. And something that I said during a breakout, which is that, you know, what we're trying to do is, you know, do a little carbon dioxide removal on top of a huge noise, which is this 10 gigatons of CO2 every year. So it's a tiny signal on top of a huge noise. And that's going to be pretty tough to determine. So what do I think is needed? It's sort of roughly what Matt had said. I think we need tracers to measure the physical parameters like gas exchange, the residence time, the circulation, and the mixing. And we need biogeochemical measurements, carbonate chemistry, trace metals, and nutrients if we're doing, you know, if we're grinding up rocks. And then we need models. We need high resolution regional models that are calibrated and validated with field data. We need global models to look at, you know, maybe the best places for deployment, look at efficiencies and side effects like Manon was showing in her kelp studies. And then we need a way to generalize this, right? Because we're not going to do this in all the different locations of the ocean. So some way to generalize this to other parts of the ocean, either through machine learning or statistical methods or whatnot. But anyway, so that's it. That's my summary, which is the same as your take-home messages. Thanks.
So it's a great presentation. How many of these uncertainties go away if we are sequestering terrestrial biomass instead of kelp?
Yeah, I guess that's then is a different problem. Then it becomes a durability problem of, you know, how long does something that you sink to, I assume it gets to the bottom, how long does it stay? Yeah, so it's different.
David, provocative as always. Question. I get what you're saying about how carbon removed from the surface is not replaced by atmosphere, but on a global scale over a period of, say, a few years, you think that's still the case?
Yes. Well, I mean, once your water mass moves away from the surface, it's going to be, you know, ineffective for taking up carbon, at least for quite a while.
Hi, Ben Swainbank with Coastal Carbon Solutions. So yeah, in the beginning, you kind of introduced the kind of the different rates of uptake, right? And how difficult it is to measure that. But you also have the case where it doesn't get uptake at all, right? Where the downwelling event or something occurs. And do we have, you know, and that seems from the CDR perspective, kind of the most interesting case, right? And certainly quantifying that percentage. Do we have anything at all of knowing kind of with what kind of frequency that might be occurring?
Yeah, people have done modeling to look at that, and Manon was saying earlier, you know, her efficiency ranged from very, very low to something closer to 80%. So there are cases where that happens. Yeah, if you're interested, you should talk to her. Yeah.
Okay, we have an online question here. In many introductions, it is said that 30% to 37% of all historic emissions have been taken up by the oceans. So wouldn't removing oceanic CO2 be removing historic atmospheric CO2?
Well, I guess we're not really removing CO2. So in the case of alkalinity, you're just shifting it to carbonate and bicarbonate. In the case of kelp, hopefully, what we're doing is we're turning it into organic carbon and putting it into the deep ocean. So we're not taking it out of the ocean, per se.
This is Jaime Palter, and I'm going to push back a little bit and say that I think it's like a little bit pessimistic to say that the carbon wouldn't get into the water eventually, because there are places and water masses that spend, in a 10-year period are in the mixed layer for some number, 200, 300 days. So in some probabilistic sense, it will be in the mixed layer over a decadal timescale long enough to equilibrate. And so I just want to push back and see
It's fair. It's fair. I think on short timescales, though, I mean, there are, you can say, okay, and on the timescale of these projects, maybe, you're not going to remove that CO2.
Here's a question from Brendan Carter online related to the last question. David, is there no value in mitigating ocean acidification?
Well, so it's a trade-off, right? So if you reduce the CO2, then you raise the pH. But once you take up the CO2, then the pH goes down again. Maybe it doesn't go down as far as before, but it's pretty close. So you can't have what's the expression? You can't have your cake and eat it too.
Hi, Greg Rao, Planetary Technologies. What about the case where surface seawater is super saturated in CO2 and you don't have to worry about the flux of CO2 from air to ocean? You just need to take up that excess CO2 and prevent it from degassing to air. Is that a simpler problem or not?
Well, I think we talked about this in our discussion group yesterday. I don't think it's is simpler in the sense that you think it is, because you still have to deal with the circulation and the residence time and the gas exchange and the carbonate chemistry, right? So I don't know why it would all of a sudden negate those issues. You still have to track, the flux, and it still doesn't happen instantaneously.
From the ocean to air by adding alkalinity.
Yeah, but you've only reduced it as long as the water mass is at the surface, right? And it's the same problem with uptake. It's going to take up CO2 as long as the water mass is staying around.
Do we have time for one more question? Or?
Yeah,
Okay. Is it clear? Saving it for the panel? Cool.
Great. Well, thanks so much, everyone, for participating in this meeting and for, yeah. Is the mic working there? Okay, great. All right. So my name's Galen McKinley. I'm at Lamont and Columbia University, and I want to talk about the time-space scaling of uncertainties in the ocean carbon uptake. And I come at this from the perspective of that baseline of trying to understand what the ocean is doing right now with respect to absorbing fossil emissions from the atmosphere. So variations on the global carbon budget plots have been shown multiple times before. This is the last year's summary. And so just to make it clear to everyone that the ocean is a big part of the global carbon balance right now. And so we see on the left-hand side, the sources and the fossil and in the land source, and then the sinks in the ocean, land, and in the atmosphere on the bottom there. On the right-hand side are the cumulative sources and sinks since 1850. And from that, we can see that only the ocean is a net sink of carbon from the atmosphere since the pre-industrial, because the land source early in the industrial era has been balanced by the land sink. So it's the ocean that's really mitigating the fossil emissions for us. So how does this work? It's very Okay, there we go. So in order to understand how this works, we really need to put ourselves in the perspective of separating the natural carbon cycle from the anthropogenic carbon cycle. And this is how our estimates are made in the current day. And so I want to review this and make sure we're all on the same page with this. So the total carbon in the ocean, which are individual molecules are not distinguishable from each other, but the total carbon cycle can be thought of as the separation between a natural carbon cycle and an anthropogenic carbon cycle, with the natural carbon cycle having existed in a global mean steady state since the pre-industrial time. And this is the part of the carbon cycle that includes the biological pump, includes inputs from rivers of DIC and DOC, and the overturning circulation. And it is this natural cycle that dominates the total profile. You can see the blue profile is almost the same as the dashed white one. That's the total and the natural. So the fact that there's more carbon in the deep ocean is due to this natural cycle, due to that biological pump and the overturning. On top of that, we are adding carbon to the ocean, essentially as Henry's law operating on a global scale. We are exponentially increasing the PCO2 of the atmosphere, and that is driving carbon into the ocean. And that profile has the opposite sign with depth, right? It is decreasing downwards instead of increasing downwards. And this tells us that most of the anthropogenic carbon is in fact stored in the upper ocean, 75% above 1,000 meters based on recent estimates. And that is this anthropogenic carbon sink. Of course, we're going to need to change what we call the anthropogenic carbon sink with CDR happening. But what we know now is the anthropogenic carbon sink is the uptake of the ocean simply by the fact that the atmosphere is going up. The atmosphere is going up exponentially. And not to belabor that point too much, but I want to show you this image. This is the data of the global mean atmospheric PCO2 and the global mean PCO2 from observation-based products and models, which I'm going to talk more about in this talk. You can see from this plot that just over the last 35 years or so, the ocean is chasing the atmosphere. That's what's going on. The ocean is trying to equilibrate with an atmosphere that has more and more CO2 in it. And so the ocean is responding to the delta PCO2 that's created. It's taking up carbon, taking up carbon, taking up carbon. And important to note that it's only this modest delta PCO2, as David introduced. It's that delta PCO2 that drives the sink. Global mean, that's only 5 to 10 microatmospheres, which is pretty darn small, okay? But this is what we're working with. This is the ocean carbon sink that we're dealing with right now. And it is of a magnitude of about 3 petagrams of carbon per year in 2020. Okay, that is a huge amount of climate service that the ocean is already providing to us. And if we look forward, these are CMIP6 models under different scenarios. This is showing emissions. I didn't have the atmospheric PCO2, but it can easily be translated into PCO2. We can see that the ocean carbon sink basically to first order follows the emissions, okay? So the ocean carbon sink right now, I said, is about 3 petagrams at about 2020, but you can see it's gonna grow if we put more carbon in the atmosphere. It's gonna decline if we put less in the atmosphere. The ocean is gonna very quickly respond to the atmospheric growth rate. And so when we're talking about mCDR, we have to remember that these fluxes are this huge background that is the key thing that's actually modulating climate change, and that any variability or uncertainty in these fluxes are going to swamp our signals of MRV. And even more importantly, if we lose our capacity to quantify the natural, there's anthropogenic sink, which is, my terminology is getting mixed up here. If we lose our capacity to quantify this part of the sink, we're never, then that's a real problem. We have to also think about mCDR and the work we're doing here as how do we improve our understanding of this baseline, as well as figuring out how do we quantify individual projects And then ultimately, even though right now mCDR is far, far below that 3 petagrams of carbon per year, particularly if we really get to the numbers of 5 or 10 petagrams that Simon Freeman was talking about yesterday, then it's quantitatively, comparable to this ocean carbon sink. And as scientists and business people, we're going to need to be able to tell the world that you put this much carbon into the atmosphere from emissions. This is what went into the ocean because of the atmosphere going up or coming down. This is the natural sink of anthropogenic carbon. And this is what we did in addition. And this is why the atmosphere looks the way it did. Even though that's not the goal for the next 5 years, we do need to get there. We do need to keep that in mind. Okay, so I want to talk about the ocean biogeochemical models and these PCO2 observation-based products and give you some idea of where we are right now with our quantification of the global ocean carbon sink and the uncertainties. Okay, so ocean biogeochemical hindcast models. This is what Matt Long talked about and really explained so nicely this morning. These are simulated circulation and carbon processes that we use to estimate air-sea fluxes. And the other approach that I want to talk about are products, observation-based products. These are derived from ocean PCO2 data at large scale. And so we map in the green map there, we map the PCO2. And then using the kinds of the Wanacop 92 or other kind of relationships to wind speed, we can calculate the fluxes shown in the flux map on the bottom. And you can see there that where where we have dark greens on the top map, where the PCO2 of the ocean is higher than the atmosphere, we have carbon coming out of the ocean, and the reverse where we have PCO2 of the ocean less than atmospheric, where we have a sink. And so it is really this delta PCO2 that drives the sink. And so therefore we need to know what the PCO2 field is of the ocean, and would like to know it every month, at least for as many years as possible. How do we know that? Well, we use data, and most of the data that we use right now is not from autonomous vehicles, it's from ships. Ships that started running in, few with Takahashi's work started in 57, and increasingly to date, we have research ships, volunteer observing ships that are out there doing transects with automated analyzers on them, measuring PCO2. And we have the SOCAT, not base-funded, research-funded effort to pull together these data into the SOCAT database. And so we have access to these data, and every year it's updated, okay? And you can see from this map that, well, clearly there's a lot more data in the Northern Hemisphere than the Southern Hemisphere, because that's where more ship traffic is. You can tell that that would be a problem. But remember, this is all 65 years of data. If we actually look at any one month, this is what we get. In June of 2016, which is a representative month, this is the kind of data you actually see in SOCAT. We have a few transects here in the Pacific, a few in the Atlantic. This is extremely sparse data. In fact, the coverage of SOCAT since the 80s is about 1.5% of all 1 by 1 degree or 100 by 100 kilometer grid cells of the global ocean, okay? So it's quite sparse, right? So how do we fill in the gaps? How do we turn this into full coverage, time evolving flux maps? Well, we do have full coverage data from satellite and from some climatological estimates from in situ observations that relate to PCO2, chlorophyll, SST, for example. And we can use machine learning to build statistical relationships that connect the PCO2 where it's observed to those other variables. And then with those statistical relationships, we can predict PCO2 at all points in space and time. And from that PCO2 field, then we can calculate the flux. Okay, so these are the products that David showed in his plot that we can compare to our models. Here's my plot of the comparison between the hindcast models and the observationally based products. You can see that the means of these two to first order, they pretty much agree in the rough order of the sink, but the uncertainty bounds are really large, and we have this apparent divergence in the recent years that has yet to be explained. So, first order agreement, we can quantify the ocean carbon sink, but the uncertainty is on the order of at least half a petagram plus or minus. And we want to do better, right? Because we want to do better at closing the global carbon budget. We want to do better at reducing these uncertainties. So that's what I want to talk about here, some of the ways we're working on reducing those uncertainties. So the first question I told you that these PCO2 data are extremely sparse. Do you believe that these products can give you robust flux estimates based on that really sparse data and this machine learning magic that people are doing? Well, when I first heard about this work, I didn't believe it. So I decided we needed to test these reconstruction approaches. And we did that by using climate models. So we said, well, in a climate model, we actually have a full field PCO2 field. So that's shown in the top left there. We can sample that model as the observations and reduce the data down to what would be available in the real world. We can apply a reconstruction approach, in this case, the neural network SOM FFN of Peter Landschutzer, to build a reconstruction in the context of this model world. We can estimate the reconstructed PCO2. And then we have step 4 on the far left there that we can only do in this model space is that we know the truth. We can compare back to the truth and we can say, how well did we do? Were we able to reconstruct the full field PCO2 as originally modeled? Now, it's important to emphasize that this effort is not about estimating real-world PCO2. It's simply about testing the methodology of the reconstruction, right? And so we do this, we do it 100 times because climate models are imperfect and we want to have the variance of the climate system there. And we can statistically assess how well these reconstructions do. And to my great surprise, when we first saw it, the global biases are very low in these reconstruction approaches. It does appear that we have enough information, even with only 1 or 2% of PCO2 data. We can fill in the state space of the relationships of PCO2 to SST and salinity, chlorophyll, and build global maps of PCO2 from which we estimate flux. It has a global bias that's basically 0. That's really good from the global carbon budget perspective and really encouraging. Now, for this crowd, it's really important to emphasize that that does not mean that there are not large regional uncertainties. So I draw your eye to the Southern Ocean, where there's large blotches of blue and red. Those are large mean biases from this approach across the Southern Ocean. Average it all out and they go away, but locally, large biases still exist. We can also evaluate these reconstruction approaches in terms of their ability to capture the seasonal cycle. And this is a correlation map between the original model and the reconstruction. And you can see that for seasonality, most of the correlations are greater than 0.8. So we can do quite well in most of the ocean at reconstructing the seasonality of PCO2. Decadal variability, much more challenging to reconstruct. We just don't have enough data to do that as well. We can also do this for amplitude. We can also do more tests. I don't have time to get into that in this talk, but I just want to leave you with the point that at large scales, the air CO2 flux mean and seasonality can be robustly reconstructed from observations, and this is on 30-year timescales. However, regional biases can still be quite large. So do the ocean models also have low bias, right? That's the other side of this that I was trying to get at. And I don't have time to show you all the analysis on this, but the basic answer is no. I think that the models have large regional biases, probably related to their poor representation of ocean circulation at a 1 × 1 degree nominal resolution. So here's just some evidence of that. This is a comparison to data, GLODAP data, which is DIC and alkalinity turned into PCO2 using the equations, and LDEO, partial pressure of CO2 observed autonomously. So these are about 9 different ocean models. And on a Taylor diagram like this, we have a correlation going around, and the standard deviation is on the bottom axis. And the star there is if the model was perfectly capturing that independent data, you would lie on that star in the bottom, at the bottom there. And you can see that the models don't do a very good job, essentially. So their correlations with GLODAP and LDEO is only about 0.5. And they sometimes overestimate and sometimes underestimate the scale of variability compared to these 2 data sets. So there's a lot of spread, and this is just one example. We have other examples that demonstrate large regional biases in our current models. Okay, so I've told you that the products can capture the mean and seasonality. I've told you that the ocean models have substantial errors. And so then we asked, well, could we use machine learning to correct the models with the data? Since our goal here is to get the best possible estimate of the PCO2 field, can we make some progress if we put the strengths of both of these together? And that's a new product that we have out called LDEO HPD. So that's the hybrid physics data approach. So in this approach, what we're doing is we're saying, well, let's recognize that these models, they're not perfect, but they do tell us something about what ocean PCO2 does, how it varies seasonally, how it varies interannually. So let's take that as a prior guess. And then we can use our machine learning to calculate a misfit of the models against the observation, so that we're not going to be reconstructing the actual PCO2, but we're going to be reconstructing a correction to the models. And so then we use our machine learning with our full field driver data based on observations to find that misfit. And then our final estimate is the mean across 8 different models to which we have done this. We use an XGBoost algorithm, and all the data is real world data. So important to emphasize that each model and each month gets its own correction. And these vary substantially across the different models. So just choosing 2, MPI and CNRM, we see that in DJF, for example, MPI needs to raise its PCO2 by more than 100 microatmospheres in most locations across the Southern Ocean, while CNRM needs to lower its PCO2 in most locations by on the order of 25 microatmospheres. So so from the point of just understanding model biases, these fields also have interest, and I'd be happy to talk about that with anybody later. Another thing we found is that the climatological misfits are much larger than the interannual misfits. So if we look at how big the misfits, we find that the dominant part of the total misfit is monthly. Okay? It is not January of 1995 compared to January of 1997. That's much smaller. The models have mean, state, and seasonal biases that this approach is correcting. And so, and you can see that here on 2 different color bars in microatmospheres. The Princeton model, for example, needs corrections on the order of 25 to 50 microatmospheres positive in many locations, but yet the standard deviation of the interannual corrections are mostly on the order of about 5 microatmospheres. So mostly this is correcting the seasonal and the mean of the models, which I already told you that the products do quite well on. Okay, so if this climatological misfit dominates, we can say, well, if I only corrected my models just with that climatology, how much better would I do than just the models themselves? So I do that with this LDO, this climatological test, which is the dashed cyan blue line there, compared to if I use this interannual correction. This is a time series of the CO2 flux from the resultant. And you can see that both approaches look pretty comparable to the other products that are out there. There's about 6 or 7 now, other mostly machine learning based products. The one with the interannual correction has more variability than the one that's climatological, but the basic patterns are quite similar. And if I go back to my Taylor diagrams here, and I ask how much improvement based on these independent data do I get with just a climatological correction, you can see that I do a lot better against the independent data. Instead of being at 0.5 with the original models, now I'm closer to like 0.85 against these independent data, and slightly underestimating the variance, which isn't really a surprise. If I then add the interannual correction to this, you can see that it is better if I add the interannual corrections, but it's not a lot better. The main part of that improvement is, again, the climatological improvement on the models. And if I compare to the other data products, the final result is modestly better than the other available products out there. And so the last step that I will say is that because we've now shown that the climatological correction is the main part of our benefit here, we can use that climatological misfit to extend our estimate of fluxes back to 1959, the beginning of the Mauna Loa record. And so now we have a full coverage, 1959 to 2020, estimate of the air CO2 flux based on observations with the climatological correction for 59 to 82, and then interannually after that. And this yeah, so this product will be in the global carbon budget for this year. So that's kind of exciting for our group. So this is some progress on how we are moving forward, understanding models, understanding these data products, using machine learning to make the most of sparse data. But to end with, in the last few minutes, I wanted to take some time to compare the spatially resolved estimates that we're getting from these models and from these products, because I think that's really, really relevant to this question of MRV. How well do we know this baseline at the local scale, at the 1 by 1 degree resolution scale? So what we've done here is we've taken, in the top left, we've taken 2 different products and different those. The bottom left and the top right are the different products versus one of the models. It doesn't really matter which one. And then the bottom right is model versus model. So you can get an idea of the range at every point when we compare these products and models. So you can see that for the long-term mean, 1990 to 2020 mean, which is what I'm showing here, the products look a lot more similar to each other than do the models to the other products or the models to themselves. So that is consistent with these products being able to represent the mean state reasonably well and the large mean biases in the models. And so, in most parts of the ocean, the uncertainties here, just based on this, very rough estimate of spread, is at least 2 moles C per meter squared per year in terms of this baseline. Now, if I just look at 1 month, I chose May of 2010, just randomly, I see, essentially the same story, but the uncertainties are larger. It's still, it's saturating at 2 moles C per meter squared per year in many locations. The products are closer to each other than the models are to each other or to the products. And if I look locally, say on the US East Coast, it's the same story. It's just a zoom in here. We have very large uncertainties. So for the spatially resolved, we don't have a good, a great control on what that background flux is. These are large uncertainties that I think would swamp any direct estimate of from MRV. And so one needs to think about how these uncertainties would be propagated into an MRV system. And then the last thing I'll say there is, if you might say, well, yeah, okay, the model's not perfect, but if I just say I grew my kelp in it, then I could get the difference between the model without the kelp and the model with the kelp, or the model without the alkalinity enhancement, or the model, right? Do you believe that that's correct, given the mean state errors you're seeing here? Do you believe the capacity to get that delta accurately in the context of, large mean biases? Do you think the processes underlying the response to the alkalinity enhancement or the kelp are well represented? That's the question you have to ask. I mean, you don't have to have a perfect model. You're never going to have a perfect model to do these studies, but you at least have to have some belief that the underlying processes are accurate enough to be a useful tool for the question you're asking. Okay, so those are my take-home messages. Large scales, the ARC mean, CO2 flux mean and seasonality can be robustly reconstructed, but with large regional biases. That we can use machine learning to leverage the complementary strengths of models and data and go back from 59 to 2020 with data products that give us a reasonable estimate of what's been happening. And then again, despite global convergence for the long-term mean, these regional and monthly estimates do diverge quite widely. So thank you, and I'd be happy to take your questions.
One question.
All right. Oh, we have the panel.
Mr. Whittle, just in a big picture cartoon, the DIC gradient, you get the natural and the total shifting because of anthropogenic input. So the assumption is that there's absolutely no change in the biological carbon pump with that side of your cartoon over the last 100 years or something like that. what supports that?
Well, that's absolutely right. I mean, all the methods with which we estimate anthropogenic carbon uptake by the ocean, the effort is to remove in the data analyses approaches, a steady state biological pump is removed. I don't think that, theoretically one can think of many reasons why the biological pump might have changed, but we don't have evidence to support that it has changed because, we're in a situation where 5 to 12 petagrams of carbon per year remains our estimate of how big it is in the first place. We can't see change over time with that. The satellite record is too short, right? So it's sort of this combination of we don't have evidence that it has changed and also the atmosphere has gone up by 40% since the pre-industrial. And so the driving force, we can explain what we do observe very well without the biological pump. There's not a missing term in there that is driving much of the uncertainty as far as we can understand it. But the other thing I'll say is it doesn't mean that the biological pump won't change in the future. And it doesn't mean that we don't need to understand the biological pump to understand how the carbon sink evolves over the future. So I totally, we need to do that work. We need to understand these interactions, but we just don't have evidence that it's been important quantitatively yet.
Okay, I'll get them up in a sec. No problem. If it's on Google, no problem. Yep, it should be fine. Let's see. Yes. All right. I'll do it from here and you can speak there.
Can I go now? Yeah, okay. Hello, everyone. This is Hongjie Wang. I'm an assistant professor at the GSO. Welcome to GSO. So you may have seen this paper. Somehow this paper become a superstar for this OCB. Level to see the presentation, the other figures. I want to add a little bit of detail on the work I did when I was a postdoc last year, working with Jessica and Darren and Brandon and Matt. It's a wonderful team, and teamwork makes dream work, as my son told me. So I want to add a little bit of detail about the TA addition. So for this simulation, which is a pure simulation, nothing really happened in the field yet. So the TA addition rate is 1.67 multiplied by 10 to 10 more per year. So this is not just a random number. This number based on some real situation. Maybe So based on the technique Matt mentioned, this amount of activity you can really produce them based on about 30 offshore wind turbines. So a pure green energy, you don't want to burn fossil fuel to produce the energy to remove air CO2, right? So that's why we picked up this number. And so all the addition is on Univ pass. You can see on the right side, the green points there. And so the reason is the water came from the south and through that Univ pass and go to the Bering Sea, eventually get out of the Bering Strait. So so I want to put this other simulation based on bearing C10K model. As you can see from the title, the resolution 10 kilometer. So put the 10 kilometer in the context of a daily life. So the entire Bering Sea, not Bering Sea, Narragansett Bay on the right side, we say Sea Rhode Island. So the entire Narragansett Bay is about 300 square kilometer. That means if we want to use that, the resolution of a Bering 10K model, there are only 2.5 or 3 grids to cover entire Narragansett Bay. So that's the scale of this very regional model at the current situation. Can you move to the next slide, please? Okay, so I just changed the slide a little bit based on David's explanation. So, after you add alkalinity, you can reduce the CO2, but that's not a CDR. CDR only kick in when you really move the air CO2 through air exchange into the ocean. So the first panel shows the T difference between the simulation after you add this alkalinity. You can see so a lot of things. First is a time series. You can see the seasonality. You can also see the spatial variability. So in the winter time, generally in the Univ Pass, the water runs like a 10 centimeter per second, very fast. It can remove the water that mitigated alkalinity to much wide area. But in summer, it's more calm. The water current is very slow. You can see TA accumulated near the Univ Pass addition side. And so, and then after you reduce the CO2, you will have a CO2 flux, but it takes some time. Eventually, you can see the DIC difference again between the simulation and the control simulation, and between the experiment and the control. You can see the DIC difference. It's much mild compared to irradiation. Okay, and also it have time lag about a few months when you see the signal. Again, that's how long it takes the ARC equilibrate. Okay, and we then did a lot of mathematical calculation. So I didn't show the equation, but the CDR efficiency, the CDR efficiency we calculated is, the definition is the simulated DIC increase versus the theoretical maximum DIC after you add alkalinity. The efficiency 0.96 is almost 1. That means if we treat it like we can treat it basically like a box. There's no alkalinity leakage after you add alkalinity. All the alkalinity, I mean, 96% of alkalinity played its role by removing the air CO2 if you give enough time, a few months and a few years. By the way, we did a simulation for 10 years. Okay, I can stop here.
Okay, I'll go next. Hi, I'm Jaime Palter again. It's been great to meet so many of you, and honored to have put myself on this panel. Anyway, I kind of wish I hadn't done any slides because I just wanted to say a few like high level thoughts that I've been having, like zoomed out a little bit.
Oh, sorry.
I think that's the final one. Yeah, I feel like, you know, we're all asking really, everyone here has been asking really interesting questions. And I think that's one of the goals, is really to ask the questions and set us on a path of trying to figure them out. And so I thought I'd start more with questions than answers. I also wanted to emphasize that like one thing I love about oceanography is all the, what Hongjie just said, teamwork makes the dream work. Hongjie was on this boat when we went to go meet up with the sail drone, which I'll talk about a little bit. So the questions that I thought this panel could address to some degree is, can I have the stand up mic? I need it as a crutch. So I really think that there's an interesting question that has to do with scale, about how we create MRV techniques that bridge scales from like these controlled field experiments that David Koik was talking about, that target like 100 to maybe 1,000 or 10,000 tons of additional CO2 uptake to the gigaton scale, which is still really an abstraction. I mean, that's the scale of our, now we have to create a name for this because I don't think we're going to call it the natural anthropogenic sink. I think maybe we should call it the non-engineered anthropogenic sink. Okay. And we need things that will take us through these different scales of intervention. And so my take is that autonomous vehicles can be one, but not the solo tool to help us make that transition. So other questions that I have is what counts as confirmation that mCDR worked? Like, what do we have to measure? Do we have to measure the additional CO2 removal from the atmosphere, as David, I think, was arguing to some degree, that, or can we? And then via what technique? Is it enough to measure the delta PCO2 changing between the atmosphere and the ocean and say, okay, well, the bulk parameterizations are pretty good because smart people have spent their career figuring out what Wally Broker figured out with 1 point. Now we have people's careers have figured that out even better. So is bulk parameterization enough? Do we need to do eddy covariance like they're doing over the salt marshes that we heard from Patty? Do we need to measure the DIC increase in seawater, or is it enough to say the flux happened? Do we also need to see the inventory change on these scales? Because these, as we set the bars higher and higher, we're creating a conflict between the participation of people who want to get involved and like this perfection ideal that we may never achieve. And so then is it enough to trust that the process works because we understand what the process is? So if we measure that the alkalinity increased, can we trust that that will eventually drive more CO2 into the ocean from the atmosphere? If we're talking about biotic interventions like kelp sinking or ocean iron fertilization, would it be enough to accept that the export production enhancement happened across a given depth or density? And these are all questions, not answers, because I don't think I know those. Okay. But what I wanted to promote was this idea of autonomous vehicles. Oh, thanks. Helping bridge that gap. So Galen set me up very nicely by showing the SOCAT database in any given month is virtually empty, but we can add our autonomous vehicles and start monitoring that in a persistent way. And with the ASV CO2 sensor that Adrian Sutton helped develop, which can be carried on Wave Glider and Sail Drone and other autonomous vehicles, maybe eventually we can add to these. So one thing that, so this is work that was done by my student, Sarah Nickford, who was also featured in the previous photo, comparing the ocean PCO2 directly measured from Sail Drone in dots, which you almost can't see because the background colors are that Landshutzer data product. This isn't a really hard place to measure that has essentially no wintertime measurements, and yet those machine learning methods are doing quite well, at least in this region, which is pretty well measured. It's not perfect. And the right is the CO2 flux from that bulk parameterization, that gas transfer velocity. This added as much data in February, in the month of February, in 19 days of Sail Drone, as had been collected in the Gulf Stream region in the month of February since measurements began, one Sail Drone. This year, from December 2021 till August 2022, we had between 1 and 3 Sail Drones in the Gulf Stream all year. And we collected hundreds and hundreds and hundreds of atmosphere and ocean CO2 measurements. And so this can be a game changer. I really think it can. And then if you click one more. Too long. I just want to reiterate something Lynn Mew, my postdoc, showed, which is you could imagine, or I have been imagining, using autonomous sensors to look at experiment scale perturbations. So in that hypothetical thought experiment, where you add alkalinity to the Amazon River and monitor its influence in the plume. So hypothetical addition of 20 micromolar alkalinity in the river creates this PCO2 change in the plume. We can see the plume from space because there are satellite methods that can allow us to reconstruct sea surface salinity. So we don't have to be perfect in following a patch of water in this Lagrangian way that's usually invisible. We can see where the plume is, and we could send drones to crisscross it before and after an intervention. So that's kind of the field scale, but then you could imagine these autonomous vehicles being nodes in a global scale monitoring. And so with that, I will close and hand it to Dasha.
I don't have any slides. I'm sorry. I'm jumping late on this panel train. Just give a brief introduction of what's my research been about and how it relates to MRV. So I'm from Dalhousie University, Dariia, Atamanchuk. I'm a research scientist, and For years, I've been involved in the sensor and platform development to observe natural and anthropogenic both carbon cycles. And now looking at the ways of applying that knowledge to be of helpful MRV. And one of my roles as a IOCCP steering committee member responsible for instrument and sensors, we're taking part in the intercomparison studies that are looking to assess the current state of technology, but also to promote development and intercomparison studies aimed at having that interoperable space in terms of technology. Also, large part of my work is testing new technology that's out there. It's not ready for market yet, but through the years of collaboration between industry and academia, I've been involved in a lot of studies with the sensor manufacturers. So I wouldn't list all my, disclose all my involvement, but it's mainly on this, I would say, voluntary effort where the sensors are willing, the companies are willing to provide the sensors and the sensor platforms for us in academia to assess the quality of the measurements that they provide, but also help with advice and help with ground truth in the sensor data. And I think that that collaboration that's ongoing has been beneficial for both companies, but also academia, and that promotes the sensor development. And then finally, I want to mention the work we've been doing with Planetary Tech, another disclosure. We've been involved in this field experiment that Will was mentioned about. And in that, we've been testing at least 2 prototype alkalinity sensors, which showed really good preliminary results, and also a bunch of new pH sensors that's probably not on the list on any of the directories that have been shown here, but they show a lot of promise. But again, I want to emphasize that only through this collaboration between academia and private sector, we can achieve technology level at a scale that will be useful for greater use, not only for individual studies. Yeah, and I'm open for questions.
Okay, I think we can open up for questions. Questions from the audience.
This is Randy Bundy, University of Washington. This is a question for Galen, but probably others could answer. I remember at the OCB meeting in June, seeing some of your slides, and I was like, oh, I feel pretty good actually now about like our ability to understand like baseline air sea CO2 flux. But now when I'm thinking about it in a marine CDR context, and I saw some of those regional mismatches that are like 2 moles carbon per meter squared per year, which is like equal to the biological pump. I'm feeling sad. And so I guess I was wondering how you feel about our ability to constrain those on like a more regional level related to either an experiment that would be deployed or in like a, yeah, I don't know, a bigger CDR sense.
Yeah, I mean, I think that, okay, so from the global modeling perspective, I think a lot of our models haven't received a lot of attention in recent years, in part because of other priorities. And I think that we need to highlight these large regional discrepancies from data products that we now believe can constrain regions. And I hope that drives the model development, right? And understanding, I think like Victoria made the point that, you know, if you run a model at a 1/10 of a degree, you get a very different upwelling rate in the Southern Ocean than at a 1 degree. Those kinds of things could be really impactful to the net ventilation of low anthropogenic carbon waters to the surface, right? So I think that there's a lot of work to do just at that scale, some of which could be driven forward by investments in the mCDR world, right? Like we just need to constrain that better. I think from the machine learning perspective, as Jaime said, the approaches are quite powerful, more regional looks like Patrick is doing. and ultimately more data, right? So I think we can use things like the test bed to sort of assess like how much more data do we need? How much, if you did add sail drones across the Gulf Stream, how much would that change our results? So I think we can iterate by using models and observations together to improve. But I think there's probably a lot in the physics of the models that needs to be improved. That's where I would start because, yeah, that's where I would start. But there's probably also a lot in the biological side as well that could be affected, right? Because let's say we went to high resolution in the physics, we might have better nutrient supply in the subtropics, things like that. So I think we need to keep working on those things at the same time that we're looking at MRV so that we reduce the uncertainties for the background sink and that we can converge, right? To get to a point where when we have, MRV at gigaton scale, we also have a good enough quantification of the unengineered anthropogenic carbon sink that we can say, we can add them up and get what the atmosphere is actually feeling.
Okay, I have an online question from Benjamin Sands. This one, are uncertainties lower in particular locations such as seasonal upwelling areas, such that the uncertainty bounds shift and we can assume a net positive mCDR for particular methods?
David, go ahead.
So once again, I'm going to refer to Manon's study, right, where she shows where it's more effective to do these things and where it's less effective. So I would say that, if we want to answer those questions, it's really models that are going to help us, models that are informed by data. But ultimately, I think it's models that can answer those questions.
I think I'd return to this idea that at first, right, we don't go from 0 to a gigaton. At first we would do small controlled studies where we do a baseline. I mean, any controlled study, you have to do a baseline first. So I think maybe the answer is you'd go to a place that you have some background knowledge, right, where you can scope an experiment just by thinking about it. Then you'd maybe run a model, or it'd be so small you wouldn't run a model, but either run a numerical model or do a very small field trial with a strong baselining, months of data collection before you go out, data collection after it happens, and you'd see if you could detect it, right? These would be our first efforts. I can't imagine how we would ever leapfrog kind of that scale, even if it's too slow, and which it may be relative to what commercial interests would want of us. But from the science perspective, I don't see how you get past that.
Matt Eisman, Stony Brook and Ebb. David, in your talk, you showed that example of the equilibration and, after it's fully equilibrated, the pH change is quite small, so hard to detect, but at the beginning, it's quite large and detectable. And so this is a question for everyone, to Jaime's and Hongjie's talks is a place to start where, we have a sail drone cutting across a plume. We have a model of what we expect to be happening, and essentially what we're measuring as we get further and further away is, the question is, are the data we are measuring consistent with what we expect in the case of CO2 removal? And we can say that up to a certain fraction. So we could probably verify that to some percentage of removal, and then beyond that, it's in the noise. Is that at least a place to start?
I think maybe. So, initially you have this large signal, but that's not CDR, right? That's some confirmation that you've put in the alkalinity that you expected, which is important, but it doesn't say anything about what you've done to the atmosphere. And then, you've got these months of trying to figure out where this patch goes. And I think that's a nightmare. And I just don't see how you do it unless you're in a confined water body, right? Which is maybe a good way to start. Like Jaime was saying, we need these field experiments and we need some physical constraints. So, Bedford Basin sounds pretty good for something like this.
I would just add someone said Bedford Basin, I'm like, follows. So not saying anything against the sail drones, but you think about the proper platform for the proper place. Sail drone is not an appropriate platform if you want to start MRV. It's an open ocean platform. It's designed to measure a larger scale and variability. You will be looking at wave glider type, small AUV type platforms, maybe some more sensors. And I think the beauty of the smaller scale study is that because it's usually coastal, the signals are more enhanced and it's easier to measure them. So if we start small, it kind of has benefits of, for us, being able to measure that signal because it's significant because the scale of release is much smaller. And at the same time, the technology demand is much lower if compared to the open ocean studies. It's easier to detect the signal.
Hi, Libby Jewett from the NOAA Ocean Acidification Program, and I'm not sure who this question is for, maybe Galen. We've heard a lot of conversation today about Earth system models, and I know that they're great for a lot of things, but in terms of capturing biogeochemical variability in regional coast, close to the coast areas, they're not as good as we would like for them to be. And yet there are quite a few regional models also that different academic groups are running based on the ROMS platforms or FECOM or others. I'm just wondering what you all think is the use of those, at least in the interim, while we're waiting for the, the perfect regionally downscaled Earth system model where it's all, straight to the coast and covers everything. Can we use those ROMS models for this MRV work? Because a lot of this work may be happening quite close to the coast where there's a lot of variability.
I mean, I think Hongjie would have a lot to say about that too. I mean, I think, yes, I think that's a really good idea, but I think that we can't expect our Earth system models to do everything all the time for everybody at every resolution, for every point in time, past and future, right? So I do think that we need to use those models. I think that one of the real challenges is that they tend to be rather developed by an individual group, right? And not with large scale support. And, like I'm running a regional model, right? And someone else is running a regional model and someone else is, and you're struggling to keep the computer systems going and the student educated on it, right? So there's not like the benefit of the Earth system models is that we have NCAR, we have GFDL, we have these places where that's being like really a focus, but we have much less of that as a consistent backbone of infrastructure for the regional models. But I think they definitely are the appropriate scale for many of these problems.
I think I can add a little bit. So for the Bering 10K model, it's a ROMS model, and it's I think, okay, so my point is we need like combination of both regional model and global model. So for example, the Bering 10K model, 10 kilometers, it's very small compared to the big Bering shelf, right? But it's still, you can't really resolve the regional impact based on this kind of regional model. So we will see a lot of noise near the addition side, which we really want to know the impact of this TA addition on this local time scale. And so my point is, to solve this problem, we need an even higher resolution regional model. But it takes so much time to run regional model, high resolution model, and also for this regional model, we don't know what will happen to the water mesh after they move out from Bering Strait. So that means we need another layer of model try to understand the mitigated water in other area in the Chukchi Sea or in the Atlantic, eventually in, for example, what's the fate of the mitigated water in the future? So to answer the question, we need a combination of both global size model and regional model.
And I had one thing I've had some really interesting conversations about this with Katja, who I think we'll hear more about it tomorrow, and others, but the regional models are, to me, very clearly going to be the models that work for these field experiments, because that's the region and the size that they're done on, and that's what resolves the key processes and everything. But there are two main, I think, big questions come to mind. One is for a place that isn't running a ROMS right now, that's like someone's 5-year dissertation. right? To get it running, tune it, compare it to observations, make sure it works. And things are happening already. So, so there's that tension. How are we going to deal with that? And then Hongjie actually raised a really wonderful point. We had our phone conversation in advance of this, is that you run the regional model. The thing, if you're really going to measure or model flux, and let's say it's an alkalinity perturbation, because that's what has been the topic so far, the alkalinity can leave the regional model domain before the flux happens. And then what? So there's a lot of questions and challenges. And I guess that's the point, that we're starting to think about all of them together with people that have done such great work.
Greg Rao, Planetary. Yeah, to build on David's point, I mean, really what we're looking for here is long residence time in the surface layer relative to the air-sea exchange rate. And in a perfect world, you know, there would be no loss of alkalinity from the surface, and we'd have infinite amount of time to equilibrate with the air, and we'd get 100% CDR. Not necessarily, it would be easy to confirm by measuring, but nevertheless, we'd have some confidence that most of the alkalinity would resulted in CDR. So I'm wondering if there's some way we can modify the addition of the alkalinity to ensure that it stays at the surface. And we all saw this Amazon model. You know, clearly it's fresh water. Presumably it stays at the surface for some time. I don't know how long it does stay at the surface, but could the fresh water or some buoyancy manipulation of the alkalinity prolong the residence time in the surface layer to allow a greater amount of it to equilibrate with air? And again, I don't know that it would help the MRV, but we have a greater confidence that CDR, the alkalinity we added, would result in CDR.
I like that it's buoyant. That's one reason that we thought it was a good idea, right? Fresh water is buoyant. So I would note that we're like duly pessimistic in two ways, not to be, and I'm not necessarily more optimistic, but we're pessimistic that carbon stays down when we use biotic methods, and we're pessimistic that alkalinity stays up when we use alkalinity methods. Like, are we really going to get it wrong in both directions all the time? You know?
Well, I think that using the fresh water perhaps is a bad idea in terms of standpoint of buffering capacity of seawater. Seawater has more buffering capacity, so if you put it just fresh water, it will uptake capacity will be lower. So as one of the strategies to prolong the exposure time, I would choose an MRV site that has a resident, like where the surface water residence time is long enough, as opposed to using some sort of a upwelling site where it can just be mixed down without being exposed to the atmosphere. But again, it's for the pilot studies, for the Bedford Basin time studies. So have to be thinking about that when you select the MRV site too.
Yeah, I just want to add a little bit. Yes, I agree with that. So I think we need to be very careful to pick up the site at the very beginning. For example, if we add the same amount of alkalinity in North Atlantic, so water sink like in very short time. So I don't think we will see the very high CDR efficiency, even with the same amount of alkalinity. So I think before we do this like experimental deployment in the future, we may want to understand the physical water mass at the very beginning, then try to make sure the water can stay surface as long as possible.
I think I'm up. Tyler Orr, UTAS. This isn't really a question, but feel free to comment on if these numbers are encouraging, discouraging, or just ill-conceived. Just as a thought experiment, if you took the US annual oil and gas revenue, which is like 110 billion, said a consummate amount should be spent on CDR, took half of that for marine CDR and said 20% was for MVR, that would buy you 550 Argo floats a year or 12 sail drones operating year round. There's no question. Just kind of curious if, you know, we assumed we should be spending as much money taking carbon out of the atmosphere as we are putting in, and then use some fraction of that for NVR. What does that actually buy you? And I don't know, 550 Argo floats a year is
Well, I think what will help is to reduce the uncertainty in the global carbon sink, that's for sure, but it's not gonna help you with mCDR research anyway. We have to start coastal. As again, sail drones, you cannot get closer than what's kilometers to shore. Like it's not, and Argo flow is the same, like you have to go really deep. So it's a platforms for open ocean studies. You have to be careful about what you wish for, kind of.
Sure. And
But
wasn't
that's-
advocating those are the
No,
answers.
I'm just engaging in discussion, but definitely will help constrain the global CO2 flux just by collecting more measurements.
I don't know if Sildren has a limitation on how close it can get, except you need the permissions to be in the EZ. Well, no, but I mean, they were just like waiting for us to, waiting for Sildren to pick them up right offshore. So they can operate. There's many other limitations. They can't deal with waves that are taller than the wing, like big rogue waves that can turn them. They charge from solar energy on their solar panels. So Bedford Basin would be out anyway because it couldn't charge really because it's at too high a latitude. So there are problems. And not to trivialize them. We're still in idea phase, I think, so.
Yes, Leonard Bach, University of Tasmania. I was just wondering, are we making this problem bigger than it is? Because, I mean, acid gas exchange is delayed, right? But unless you do it in certain regions where you have really deep convection and it's gone for hundreds of years, I mean, who cares if it's next year or in 5 years? It's all within the time scale of where we deal with the problem, right? And I think, I mean, I'm just a bit worried that we make this topic so big that it becomes a roadblock where it actually is not such a big problem. It's an interesting problem, but I don't think it's on the priority list, gut feeling, I would say it's number 7 or something.
So I feel like I did propose a way forward. I don't know if you guys saw that at the end. So I think it's a solvable problem. And it's just we need to realize that we need to deal with the problem and the solution might not be what we think it is, but there is a solution. And the solution might be the same as the one you're thinking of, which I showed.
Yeah, but I think it's also really important to have this conversation about, maybe we should be choosing regions that are naturally buoyant, where the water maintains the residence time, like all these kinds of things. Quantifying this with models, right? You might be able to make a map, just like Siegel et al. Did of the, the remineralization depth. Maybe you can make a map of, where do parcels remain in the upper ocean for at least 2 years, right? Like those kinds of studies could be done. But I think if we have to acknowledge that these are issues, like in the iron fertilization, my understanding is in those experiments, there was very limited direct observation of net air CCU to flux because there was a lot of subduction that occurred, right? So that's what really happened.
Okay, I'm gonna sneak in one from Wiley Evans. And I think this looks like it might be for David. From an air-sea gas exchange standpoint, would it be easier to track reductions in atmospheric CO2 source regions to the atmosphere as opposed to trying to track increases in uptake? Maybe the considerations are the same, but I was thinking measured surface PCO2 would be good enough to capture the signal, and the Ravel factor dynamics would be such that the signal would have a larger amplitude than for an increased uptake.
So this is similar to Greg Rao's question for me during my talk. And so my answer is the same, I think. Which is that I think you face the same problem. Maybe the Ravel factor thing is less, but you still have to deal with the residence time of the water mass at the surface and deal with, tracking this water mass as the flux out decreases.
And then figure out how to measure it in the atmosphere over the ocean.
Ken Bissler here, Woods Hall. I want to get back a little bit, but Len, I was maybe alluding to, and Jaime was saying how you can be pessimistic because this water is going to sink before it equilibrates, or we don't get all the carbon deep enough, but we don't have to for CDR. right? If you had a discount factor of 50%, then you just work that into calculations. We also haven't talked about how quickly minerals dissolve and actually impact alkalinity if you put them in that form. We haven't talked about how much carbon gets lost on the way down to that magical horizon. But a small fraction of a big number can still affect climate and air CO2. So I don't think any of these things are going to be without their discounts, and we're never going to know them precisely. So it's good to be bringing this into the calculations. Let's be honest about it, but it shouldn't stop this from moving forward. I don't see why it would stop a market from moving forward. If you can say, I've made this effect because we measured it with our sail drone, we saw CO2 draw down at the source. And we can predict that, yeah, efficiency is not 96%, it's 50%. Seems like that works, or is there something I'm missing?
I mean, I agree with Ken. I think that's the way that we should think about it, but we need to do our due diligence and quantify that and make sure we're not using, for example, ocean models that don't accurately represent that as the basis for our estimates, right? So I think there's a lot of factors here on. And then there's an additional factor that I want to point out that I've mentioned to some of you is that every time we pull a mole of carbon out of the atmosphere, we're reducing this non-engineered anthropogenic sink. There's also a discount factor there that needs to be taken into account, and it's non-trivial. So every time you're doing engineered CDR, you're reducing the non-engineered anthropogenic carbon sink. That also needs to be accounted for.
Hi, everyone. Nick Record from Bigelow Lab. Really interesting conversation. I'm a little confused about, like, we're talking about trying to figure out where and when CDR might be effective, where it might work, where it might not work. And then seems like there's also a conversation about where and when MRV might be possible and feasible, or else too expensive and out of reach. And so I'm just curious if anyone on the panel has some intuition about whether those two space and time scales and locations overlap, or whether, you know, CDR works better in places where MRV is harder, or vice versa. Thanks.
I think there was a conversation about how these two processes are parallel. One is operational, and another one is research and something. So it's two parallel universes. We have to do both at the same time. We have to identify the sites and work with the sites that are more efficient for marine CDR, but then for the development of MRV network, we cannot just go out and use those sites straight away. We need to rely on the smaller sites where we do the research and innovation. And then at some point where MRV matures enough to be applied to the operational, at the operational level, we'll jump to operational level. It's my understanding. Like, you cannot, it's not one or the other or one after the other. These two should develop in parallel with due diligence.
Richard Dewey with Ocean Networks Canada. I think this is for Galen as well. In your plot, we can imagine that the Industrial Revolution is, like Fourier said, a big experiment. So we've been pumping all the CO2 into the atmosphere, and I know we can't track individual carbon molecules, but your profile of the anthropogenic curve would suggest that in 150 years, you said 75% is still above 1,000 meters. So in 150 years, 75% of this perturbed CO2 is still in the above 1,000 meters. So this comes back to this question about us throwing out there that we're going to do this experiment that we get 1,000 years. After 150 years, 75% has only just got down to 1,000 meters. So that's a global average. Obviously, at some places it sinks right down to the bottom, and others it stays right at the surface. So we have to be pretty careful about these numbers we're throwing around.
Yeah, I'm not sure whether there's a question in that, but I do think that well, I think we need to understand that the vast majority of the additional carbon we put in the ocean is in the upper ocean, and very little of it, mostly in the North Atlantic and some in the Southern Ocean, has reached into the deep ocean. And that, but ultimately that's the long time scale process by which we say that in 10,000 years, 85% of the carbon is going to go into the ocean.
We're talking about
Um,
different processes, right? Like
but-
most of the carbon, anthropogenic carbon is taken up through the solubility pump,
Mhm, yeah.
mediated by the global overturning circulation. We're talking about actually changing through OAE, the buffer capacity, which yields enhanced carbon uptake, and the depth distribution in that sense is, it's still mediated by circulation, but it's a very different process. It's an intervention that drives additionality.
And if we think about the biological, we're thinking about enhancing the biological pump, right, which is currently on the natural side of the thing. Now, one thing I think we also need to remember here when we think about the long time scales is that since we're operating, Henry's law is operating at the global scale here, the surface ocean will re-equilibrate with the atmosphere as we pull down our atmosphere. And there will be regions where the carbon starts to come out of the ocean, particularly in the regions that are, more rapidly overturning. And so the carbon sink as we know it will evolve and change and become quite different than what we know now. That non-engineered anthropogenic carbon sink is going to change as we mitigate, whether by engineered methods or whether just by cutting emissions.
So this is, I thought, oh, sorry, Doug Wallace from Dalhousie University in Halifax. So the presentations were amazing in terms of full range of relative pessimism to relative optimism. Everybody recognizing that there's a very, very challenging task before us that we've just started really thinking about as a scientific community. And then with Galen's perspective on where we are after probably 3 decades of work on the the unengineered natural, no, anyway, the unengineered carbon sink. So I'm wondering if somebody out of nowhere suddenly came with a combination of technologies that would potentially address this problem, maybe they're there or maybe they're on their way. Does the panel feel we have the structures in place, the science structures, to actually make use of them? Or should we be thinking about that as well? I'm thinking especially about international collaborative structures for collaborative research, because this is a big problem. Or would we have to invent new structures for getting this type of science done, based on our experience with the unengineered carbon sink, for example? I'm wondering how people feel.
Well, I'll just real quickly, I think that for understanding the unengineered carbons, like there's quite a, through IOCCP, through SOCAT, through GLODAP, a lot, and GoShip, a lot of great international collaboration that would have the potential to spin up, but needs a lot more funding to do that, and a lot more base funding to guarantee that databases stick together and things like that. I'm mostly worried about the human capacity to do a lot of this work, right? We talk about like building ROMs. It's a lot of it is, as Jaime said, it's a 5-year PhD to get that going in a certain location. Where's how are we going to train the people to do this work? So yeah, and I'm worried about then how does whatever money is, we talk about all this money going into MRV. I don't see any of it coming back to monitoring, to adding to what we're already doing. And so we end up in a place, we can end up in a place where what we're trying to monitor, this baseline, is just peanuts compared to MRV. And then that's not a good situation. We have to think of a way to connect the two pieces and have some flows of funding to keep the baseline and understanding increasing. So. And the capacity of lab scientists, modelers, all these people. I mean, this is hard.
And then the sustainability of such program has to be maintained, of course. Like one-time investment is good, but it's not going to solve the problem. So we have to train and retain people. And that's just, alluding to your question, I don't think the international community is ready for this. There's just not such a structure in place, but it has to if we're taking this seriously.
So let's take just 2 more questions. One from the back.
Yeah, hi, this is Will from Planetary. As Doug was saying, it feels like a bit of an overwhelming problem at times. It feels maybe like we shouldn't be doing it at 4 o'clock in the afternoon. But anyways, industry, from an industry perspective, the MRV we need to generate has to be cost effective so that we can deploy it in lots of places really quickly. But I completely understand the need for robust observations pre, during, post, and what have you. And so I hope that there's an avenue, and I guess I want your perspective on how industry and this amazing academic community can work together, because there's no way we'll do it unless we find a path to meet in the middle and do that. And so I hope we can sort of chart that path. Not sure what my question is there, but I'd love your perspective.
So I'm actually pretty positive that we can do it. I think the problem is that nobody wants to fund MRV per se, and because it's going to be expensive, right? But if a few of us in this room got together and we got a lot of money, I think we can figure it out. And part of the reason why I think there are so many CDR companies and there aren't as many MRV companies, even though everybody recognizes the need for it, is that there's no IP that's generated at the end that you can just sell off to a bigger company and make a lot of money.
Okay, I'm going to ask one more question that you can all give a very brief response to. We got about 2 more minutes. While we're doing that, I would love it if all of the lightning speakers for the next session could come down here and line up along the wall so that we're ready to roll, because we're a little behind. So this is a question from Brendan Carter, a nice little thought question to end this on. We've now heard from many experts on the utility of various approaches to MRV. Based on these presentations, which approach, other than the one you presented on, are you most excited about as a tool for MRV, and why? Go.
Loaded question. And I'm not even sure I totally heard it, but which MRV approach am I most excited about? MRV, not CDR. Is that right? Okay. I think we're still at thought experiments and then to regional models is where I would go with that. That's like free association. You're passing. Oh man, that's an option.
I guess I'm a modeler at heart. I'm excited by the ideas that Matt Long presented about, adding data assimilation and adaptive sampling to our models and really building that out in a rapid fashion. And I'm encouraged to hear that he thinks it's doable in the timescale of years.
So Doug mentioned something about amazing technology. What I would like to see is a perfectly Lagrangian sensor that could measure at levels that we can't even imagine.
I think I would prefer time series monitoring.
I like the natural analogs too.
I like data assimilative modeling because it combines models and observations in some really good product.
I think these are the ones from the first session. Is it okay? I could just put through them. People don't forget to. Oh, you're totally fine. Does it cut into my 3 minutes? No, okay. Cool. Okay. Excellent. Thank you. Hello. All right. Hi, everyone. My name is Anna Hughes, and I am from Oregon State University working on the Regional Class Research Vessel project. So the U.S. academic fleet will soon have 3 new regional class research vessels, with one, the Narragansett Dawn, which you can see over here on the right of the screen, being operated by the University of Rhode Island for an East Coast Marine Consortium. The 3 vessels are under construction in Louisiana with major research facility and equipment construction funding provided by the National Science Foundation. So the first of these vessels, the RV Tani, located in the center, will be operational on the US West Coast in 2024. So a future requirement for marine CDR research will be access to platforms that provide an ability to track marine CDR impacts in coastal ecosystems in real time. And so in addition to tracking the marine CDR impacts, these vessels will also, tracking marine CDR impacts in ecosystems in real time. And so this is a picture of the RV Tani under construction in Louisiana. So these 3 ships that will operate on the east, west, and Gulf Coast of the United States will have identical systems that contain 58 residential sensors. So residential sensors, meaning that these sensors will be operating all the time, providing data both onshore and on the ships in real time. And this goal will be achieved with a new software system called Coriolis. So Coriolis is an acronym that stands for Cruise Operations, Real-Time Interface, and Open Live Information Exchange. I know, yes, another large acronym. So the data presence that is enabled by Coriolis, the data presence that is enabled by Coriolis will not only provide access to and visualization of this real-time data, but it will also provide a means for quality control and assurance, so QA/QC, with built-in tools for real-time flagging and an alert system that will ensure high data quality. Additionally, so some of the sensors that will be on these vessels, the 2 most important ones are the Apollo ASP3 system, which measures PCO2 and PCO2, seawater PCO2, which is the partial pressure of carbon dioxide, and then the CFOX V2 sensor located over here on the sensor wall. And so with PCO2 and pH, we hope to constrain the surface seawater dynamics in coastal ecosystems, and then other ancillary sensors that also help to inform coastal CO2 dynamics are the Picaro sensor, which reports atmospheric CO2, the SBE43, which measures dissolved oxygen, the Rosser, among many other, obviously 58 residential sensors on these vessels. And so the data presence by Coriolis will also open a door to educational and outreach possibilities by connecting classrooms with seagoing scientists. So the RCRV team at Oregon State University has worked really hard to balance these science needs along with operational constraints. So the past deployment of PCO2 systems on research vessels has been a challenge, and this is due to the operational limitations. Again, with Coriolis, we hope to overcome some of these operational limitations with making access to data, open access to this real-time data. So with this robust suite of sensors, we hope to provide access to scientists to this information, along with promoting more of a virtual participation and collaboration on seagoing operations. And the access to this data for 3 research vessels traversing 3 dynamic coastal ecosystems is going to be really powerful, especially with regards to monitoring mCDR efforts and tracking sort of the efficacy, the viability scale, and viability of different marine CDR approaches in these coastal ecosystems. So if you have any questions, please contact me, and thank you.
Hi, I'm Chris Hunt from the University of New Hampshire. I'm going to talk about some sort of nuts and bolts oceanography that we've been doing. I'm an observational oceanographer, I guess. There's been a lot of really good high-level stuff, and now I'm going to bring it really local scale. So if you remember Adrian's talk this morning, she had a chart of available sensor technology, and there was a lot of empty space for DIC and alkalinity sensors. The only alkalinity sensor that was there was this one, which we've been working with, the Contras Hydrophia system. My disclosure is we had a project several years ago that we were partnered with Contras to use these. That project is over, but we still use the sensors. But I don't really have any relation to them beyond paying them to service the sensors for me. So we have deployed these Contras underway TA sensors on various ships of opportunity. The one we use the most is the Henry Bigelow in the upper left. That's base rate out of Newport, Rhode Island here. And it's just ridden along on any cruises of opportunity that we can put it on. We've also put it on the Ron Brown, on the Hi'i Aleke, I believe, and the Healy with Just Cross and a couple other vessels. But I'm showing some data on this slide from a paper that we put out last year, just using data from 2017, 2018 along the East Coast here. So you can see maps of TA distributions in the upper right. And we lay out some sort of best practices and findings about sensor performance. But we also make the point that by deploying these sensors, this bar chart is showing that when we compare the amount of data that we collected to any data that we could pull in from historical sources, be they GLODAP or any other data sets that we could put our hands on, we increased the amount of data available by like an order of magnitude. So deploying these sensors gives a pretty powerful tool for really increasing data availability. And with Ships Opportunity, there's a pretty low cost to deployment, although the sensors themselves are pretty expensive. And I'll note that they're not in any way suitable for buoys, sail drones, or any other autonomous vehicles. If you put them in water, they will die. So the upper right is just a map of all the deployments that we've done. We have a big pile of data. Some of it I'm still have to work through, but I've started to use some of this data coupled with PCO2 data from the vessels that we've deployed on to start to play around with some more esoteric calculations. So I've been enjoying making these buffering calculations. In the upper left, there's a gamma alkalinity calculation, which just enumerates the response in CO2 based on an alkalinity shift. So I think that's kind of relevant to alkalinity enhancement like we've been talking to today. And so using these data, we can sort of identify areas in the upper left in this map where the CO2 system will respond more strongly for a given addition of alkalinity. And in the lower right, in the lower left, we can see times of the year, months, where again, the response is different. And so we can start to maybe use these data in support of deploying CDR-based projects and identifying where they might be most efficient or when they might be most efficient. And my time's up, so I'll stop there, but thank you.
Hi, I'm Ian Walsh from Corvallis, Oregon, not representing anybody. I do have a consulting contract with Ocean-Based Climate Solutions, which has a upwelling pump that they're developing, hoping to get in the water and test in the near future. But I'm mostly here as a cheerleader. We can do this, and this is an image of an operational map that was taken during the Deepwater Horizon. We have done ocean observing in mCDR if we think of oil droplets. And I wouldn't recommend that we follow the same pathway we did there. It burned out a lot of people. But we have, in fact, over certainly in my careers and many other people here, we've built the tools that we need to do what we need to do going forward. We've got ocean observing systems in line. We've done the process studies. We've got remote sensing. I've sort of grayed out analysis, visualization, and prediction because we still got a lot of work to do there. But the talks today have been fantastic from my mind. Okay, so right arrow. No. Right. May save me. No, that's not me. Too far. I do. But we were out of line before. Go one more. I think I thought I was out of order in the first place. Yeah, somehow we should. So that was the we can. And my next slide was we should, wherever it went. Uh-oh. Well, I'll leave it at that. We should do this. I don't have much more of a message than that, but but we have built the tools, and I'll say one last thing. From our discussion just a minute ago, NSF was built to double the number of researchers every 5 to 6 years. We can build the people, the human capacity here going forward, but it's going to take a lot of work to do it. On the other hand, if the value of removing CO2 from the atmosphere is compared to the value of civilization, there's a lot of money available here. And I'll end on that.
All right, okay, thank you. Alex Wang from Woodside Graphic. So I'm a carbon chemist by training. I also develop sensors. So as a sensor developer, I think the one thing I haven't heard from this workshop is that it's just too expensive to do ocean observing at the moment. So we're thinking, I mean, along with many others, we're thinking about to change that model a little bit. To switch to somewhat community-based observing system. So we are building a new generation pH profiling sensor that can be used on fishing gears. So this is the prototype I'm showing on the right, and this is the target design target we try to make. For example, it has to be self-referencing, has to be low maintenance, can do most of the profiling work up to 300 meter, basically the shelf water and the coastal water. Has to be low cost on the range of $1,000 or less. Has to be a good precision. The data show in the middle is the repeated measurement over a sample, a seawater sample. The shaded area is actually a pretty good repeatability with the picture on the top is material less than $100 we made. Mostly just boards, 3D printing material. So this is kind of the capability we're trying to do. Hopefully this kind of observing network can be used for marine CDR, MRV. So we also been working on the DIC sensor for a while. There's some delay due to the COVID, but Mallory Ringham, this is the part of her dissertation. She's been the champion of the channels. This is the second version of it. We specifically target subsurface high frequency measurement. So the middle part of this plot shows a DIC profiles along the slope of the west floor shelf on the deep coral system. So you can see the very high variability. This is just 1 meter above the surface at the bottom. So this is kind of the profile. This is kind of the first of kind. We still need to correct the data a little bit, but with the limited bottle samples, the residual below, we think is pretty reasonable. The sensor can do very good job at the surface. So that's on the left, the time series at the Pocasset River on Cape Cod, Massachusetts. The in situ accuracy compared to the bottle samples is on the order of 5 to 9. So I'll stop there. Thank you.
Hi, I'm Nicola Wiseman from the University of California, Irvine. And today I'm going to sort of talk about some models a little bit and sort of an idea that had come up for me recently. And these are some very, very preliminary results to look at simulating ocean iron fertilization within an Earth system model. This is something that we've done before using a variety of Earth system models, but for the most part, it hasn't been done in about 20 years. And Earth system models, and in particular, ecosystem modeling have changed quite significantly in that time. And so for the past several years, I've been working on sort of model development side, working with the BEC model within the CESM Earth system model, as well as now with Marble. And so this is just an example from a in review paper that I have right now that is just showing one of the aspects of the ecosystem model, which is stoichiometry. So this is our phytoplankton iron to carbon ratios. We've got a version that was running on a fixed, sort of very simplified iron to carbon versus a fully variable iron to carbon informed by observations that have come about in the past sort of 15 years. Of these values, and just showing that with some iron deposition perturbation experiences, this is ranging from about one and a half some unit of iron deposition to up to 7, I think it was gigamoles per year, something like that. But anyway, when we have that fully variable iron to carbon, the biogeochemical response is a little bit dampened. So this is global POC export at 100 meters. And so this is, a thought that I've had is that we've got these newer versions of the model that have this more variable stoichiometry. So why don't we do some iron fertilization experiments with it? So here's some initial results. There's a couple experiments that I did, and this is just global NPP, POC export at 100 meters, 500 meters, 1,000 meters. And this is just a 5-year run of a 1-degree resolution model. We have the control where nothing's happening. And then I did a couple different fertilizations, one where it's the entirety of the Southern Ocean below 40 degrees south, one that's the 3 Channel Sea regions, so Southern Ocean, Equatorial Pacific, and Northern Pacific, and another one where it was just fully the global ocean with an addition that is equivalent every 31 days of about 2 nanomolars added to the surface. And you can see here is that, we're able to quantify some of this response. We see changes in NPP. We see larger changes in NPP when we have fertilization over bigger areas. And we see sort of some differences between the different levels of export. And so I think this could be sort of a valuable tool going forward. It's obviously sort of very much in its preliminary phase, but I think it could be a sort of valuable tool to helping diagnose areas of idealized deployment. Thank you.
All right, so we get a break until 4:30, and then we're going to go into breakout groups. I'm not going to get a chance to talk to you again before we have to catch the bus back. So at 5:30, there's going to be a shuttle back to the hotels. Actually, not back to the hotel, sorry. The shuttle is going to go right to Audrey's Coffee House and Lounge, where their additional ventures is actually hosting a happy hour. So if you're staying at the Fairfield and you do not want to go to the happy hour, please let us know so that we can orchestrate some sort of a carpool situation. I know there are a lot of drivers over at the Fairfield. The people who are at the Hampton, it's right in the same plaza, so you guys can walk. I also want to let you know that the change in the morning pickups is going to shift by 10 minutes. It's going to go earlier. So the early pickup is going to be 7:20 and the later pickup is going to be 7:50 because there's just been delays getting people here in the morning and we need to get people here on time so we can get started. So the bus drivers, again, they're going to leave promptly at 7:20 and 7:50. So if you miss those buses, get an Uber. And please remember, what's that? Yeah, there's lots of parking. I think it's Hampton first. I think they've been going, I haven't ridden the bus yet, but I think they've been doing Hampton first and then Fairfield. So a couple minutes delay there. And remember that if you are chairing the breakout session this afternoon, that you need to be here for 8 a.m. synthesis in the small conference room tomorrow morning. So please take the early bus. And I think that's all I have. Thank you.